online Oxford Discrete Maths and Probability seminar. So we have 2 talks this week. So one about to start, and the second talk will be at 3:30 UK time, and we'll have a break in between the 2. Okay, a couple of sort of local things. So you're all muted at the moment. This is to cut down on general noise during the talk. But you can ask questions and so on through the chat box, and Christina and I will moderate through that. So if there are questions that need asking during the talk, we'll interrupt Bhargav and ask them. Otherwise, people can ask at the end. In case it's helpful to have a local copy of the slides, I've put them up on the web page, so you can find them. It's for the second talk, just before the second talk. Okay, let's get on with it. So, it's a great pleasure to introduce Bhargav Narayanan, who's going to talk about thresholds.
Am I audible? Am I good to go? All right. Good. I'll be talking today about thresholds. And everything I'll talk about today is going to be based on joint work with Keith Frankston, Jeff Kahn, and Jin Young Park. Okay, so before I start, I should sort of say thresholds are one of, if not, the basic objects that people want to start with when studying random discrete sort of structures in combinatorial probability. But instead of jumping in straight away and sort of telling you what these are, I'll start with a couple of examples with my apologies to the experts, because odds are, if you know what I'm talking about, the first few minutes of this talk will be irrelevant. But if you don't know what these things are, it'll be good to start, assuming very little. Okay. So the first couple of examples I'll look at will live on maybe the most commonly studied random discrete structure. So we'll ask a couple of questions about random graphs in the Erdős-Rényi sense, the standard sort of setup being that you have a bunch of vertices, n vertices, and we include edges into this random graph of probability p each independently. And we're interested in what sort of things we see in the random graph as we sort of slide p along. Okay, so that's the setup for the first sort of couple of motivating examples. With that sort of out of the way, here are a couple of questions about GNP. Easy questions, but a good starting point nonetheless. So the first question that I'd like to ask is the following. When can you find a clique of size 4, let's say, inside GNP? And of course, when should be made precise. What I mean is, as I slide P all the way up from 0 to 1, we go from what looks like the empty graph to what looks like the complete graph. And I'd like to know roughly when, as I slide P along, do I start to see cliques of size 4? So that's question 1. And the second question that will also serve as a useful motivating example for us is an analogous question, namely, again, we slide P around in GNP and we ask, at what point do we see a perfect matching inside this random graph? It goes without saying that for the purposes of question 2, I'll assume that n is even because the question makes no sense otherwise. But these are 2 sort of simple motivating questions that will sort of underpin some of the results that I'll talk about today. All right. With that said, let's go ahead and answer question 1, because I promised you these are mostly easy questions. So let's start with question 1. So how might we go about answering this question? We're asking, when is there at least one K4 in GNP? And the standard thing to do when we're faced with that sort of question is to just compute the number of such copies. So we define a random variable x that tracks the number of copies of K4 in GNP, and we compute its expectation. So we know that just from Markov's inequality that if the expectation happens to be tiny, then the chance of seeing even a single one of these things is very small. So that's a good place to start. And this is a well-known and easy computation. What is the expected number of copies? It's something like, n choose 4. Those are the number of potential copies. And each copy has a p to the 6th chance of turning up, because you need all 6 edges within that group of 4 vertices to turn up. And so the expectations scales like n to the 4 times p to the 6. And if p happens to be much smaller than n to the minus 2/3, the expectation is much smaller than 1. And in this case, Markov, as I said, tells us that GNP is incredibly unlikely to see any copies of the complete graph on 4 vertices. Okay, well, as quite a few of you already know, this is more or less the truth if one computes the second moment of the same random variable. Then one can show that when p is much bigger than n to the minus 2/3, GNP almost certainly will have many copies of the complete graph on 4 vertices. And we'll summarize both of these calculations together by saying that the threshold for GNP to contain a K4 is n to the minus 2/3. So when you're much smaller, you don't see any K4s, and when you're much bigger, you start seeing them. Okay, so let's set up what I've just said in a slightly more general context. So we'll define thresholds in a more general setup, which will be very similar to what we did with random graphs. We'll start with any sort of finite ground set. We'll call it X. And we'll consider arbitrary increasing families on X, with the caveat that there'll never be empty or everything, because of course there's nothing interesting there. And also, minor clarifying point for the purposes of this talk, if you see something like an F, odds are it's increasing, whereas I think I might reserve G for things that might just be arbitrary families inside X. Okay, so F is a nice increasing family on X, and I think about the p-biased measure. So I think about selecting elements from this ground set, each independently with probability p, and I again slide p around from 0 to 1. And I'll define the threshold of this increasing family F that I'm given to be that value of p at which the p-biased measure of the event that you land in that increasing family is 1/2. So it's the p at which the p-biased measure of F is 1/2. And I'll sort of add the minor caveat that there's nothing special about 1/2, but it's the natural value to choose there. Okay. Now, a good question to ask, having just seen the calculation that we saw for K4s in GNP, is why are we calling this the threshold value? And the reason for this is a well-known old result of Baylor's and Andrews, the Bolobash-Thomason theorem, that says that actually this value PC that we just defined, the critical probability, or the threshold, as I call it, for this increasing family, if you scale your probability P around that critical value in a multiplicative sense, so if you think about how P over PC varies, if it is incredibly small, it turns out as long as you have a non-trivial increasing family, the p-biased measure will tend to 0. And similarly, if P over PC is very large, you'll have a very good chance of landing in your family. So when you scale around the critical window in a multiplicative fashion, the chance of landing in the family goes very quickly from 0 to 1. And just to make sure that we're on the same page, the slightly more general setup, of course, includes the silly examples that we've looked at so far, because in the 2 examples about GNP that we're looking at, the ground set X is just the edges of the complete graph. And considering the p-biased measure on X is the same as looking at GNP. And the increasing families for question 1 and question 2 happen to be, well, in the first case, you take all the graphs that contain a K4. So you'd like to know if you end up sampling one of those graphs, and that's clearly an increasing family. And so the first moment and second moment calculation that we did right at the start, all they say taken together is that the critical probability, the critical or the threshold for this increasing family is n to the minus 2/3. Good. Okay. So let's now go to the second question, also easy as I promised you. So the second question was, when do we see perfect matchings in GNP? So once again, it's natural to start with a random variable that just counts the number of perfect matchings. And we start by computing its expectation. So what is the expectation? Well, how many perfect matchings are there? I'd like to start by saying something like n factorial, just write the vertices down in some order and pair up every consecutive pair. But that's an overcount, certainly, because you can permute pairs around and you'd still get the perfect matching. And you can also permute the two vertices inside a pair and still get the same perfect matching. So if you account for that obvious overcount, you work out that the number of perfect matchings is exactly n factorial divided by n over 2 factorial times 2 to the n over 2. And those are the number of perfect matchings. Each one has an p to the n over 2 chance of turning up in GNP. You have n over 2 edges and you need each of them to turn up. And this number looks something like np over e to the n over 2, if you use Stirling's approximation. And the point again is that when p is much smaller than 1 over n, the expectation is much smaller than 1. And so that tells us that we're incredibly unlikely to see perfect matchings when p is much smaller than 1 over n. Or in the language of thresholds as I've just defined, what we've demonstrated is a lower bound for the threshold probability of the increasing family, namely the increasing family of all graphs that contain a perfect matching. And we've shown that that threshold is at least 1 over n. Okay. But as many of you know, that's not the truth. The truth in this case is actually something like log n over n. So the threshold at which you start to see perfect matchings in GNP is log n over n. And this is an old result of Erdős and Renyi from the 60s. And one can ask, why is it log n over n? Why is the first moment calculation incorrect? And there's a very simple explanation that we understand very well here, namely that all the way up to log n over n, you're overwhelmingly likely to see vertices of degree 0, isolated vertices. It's a standard sort of coupon collector problem to check that you need to go all the way up to log n over n to ensure that every vertex is positive degree. And you certainly need that because as soon as you see a perfect matching, every vertex is degree at least 1. So the first moment method that we just saw gives us some bound, but it's not the truth. It's somewhat further away. But before I go further, let's, as we did for setting up the definitions of thresholds, let's sort of generalize or abstract the two sort of first moment calculations that we've done. So here we just counted the number of perfect matchings. Earlier we counted the number of K4s. And let's think about doing a first moment computation slightly more abstractly. So suppose F, as before, is my increasing family. Here's a way of proving a lower bound on the threshold that is morally just a first moment calculation. So let's say that a family G, not necessarily increasing, just a family, is a witness for F if my increasing family F lives inside the increasing family generated by this witness G. And if I add up P to the S over all the elements S of G, I get at most 1/2. Then I claim if I have such a witness that I've also demonstrated a lower bound on the threshold of F, namely that the threshold is at least P. And why is that? Well, the p-biased measure of F is at most the p-biased measure of G because of 1. F lives inside the upset over G. Sorry, it's at most the p-biased measure of the upset over G. And what is the p-biased measure of the upset over G? It's at most the sum of the p-biased measures of the upsets of the individual elements of G, just by the union bound, or equivalently, you're computing the expected number of sets from G that you'd end up finding in your random set. And so the p-biased measure of G is at most the sum in point 2 of the definition. And that is at most 1/2. And so if you have a witness, you demonstrated that mu p of f is at most 1/2, or equivalently, you've shown that the threshold of f is at least p. Good. So we call the biggest value of p for which one can find such a witness the expectation threshold associated with an increasing family. So the largest value of p for which there exists a witness G satisfying these two conditions, we define or call the expectation threshold. And what we saw earlier is that it furnishes a very easy lower bound on the threshold of an increasing family, in the sense that it's the best lower bound you could hope to get just using the first moment method. Okay. And okay, it might feel slightly strange to have to look at these witnesses as opposed to just computing first moments associated with F, but this is not a strange thing to do even when you're just studying random graphs. For example, if someone asks you, when do you find a K4 with one vertex attached to it by an edge, the natural thing to look at is not the count of the number of K4s, sorry, it's not the count of the number of these graphs, but rather the count of the number of K4s. So even in some such simple examples, it's sensible to look for stronger witnesses than just the minimal elements of F itself. Okay. And so this first moment calculation furnishes us with a trivial lower bound on the threshold. But as we've seen earlier, for example, as with perfect matchings, this lower bound need not be tight. I didn't convince you that the expectation threshold for the perfect matching was in fact 1 over n, but it roughly is. But there, the answer wasn't 1 over n. The threshold was log n over n. And a rather sort of brave conjecture, very bold conjecture of Jeff Kahn and Kalai, asserts that in some sense, that's the worst thing that can possibly happen. So we have this lower bound, the expectation threshold Q of F on the threshold of F that we're interested in understanding. We've seen that it need not predict the threshold exactly. And the gap that we saw in the prediction in the case of the perfect matching was log n, or log the size of the universe over which we're selecting randomly from. And the general conjecture of Kahn and Kalai is that the threshold always bounded by the expectation threshold up to a logarithmic correction in the size of the universe. And I should emphasize that it's a really, really strong conjecture because it immediately implies some really sort of rather hard results and problems in probabilistic combinatorics. For example, Shamir's problem on perfect matchings in random hypergraphs, the threshold for containing, your favorite bounded degree spanning tree. A number of questions of this nature follow immediately if one can prove this. I should there is the caveat that the two sort of things I mentioned have since been resolved, but both problems are the proofs that were initially sort of obtained were really rather difficult. So Shamir's problem was solved by Johansson, Kahn, Wu. Bounded degree trees were worked out by Richard Montgomery. And both of these papers are sort of hard. They're long, they're sort of technically challenging, and they're serious sort of bits of mathematics. All right. With that sort of said, let me also maybe philosophize a little bit and say something about why the conjecture is hard. One sort of really big sticking point with the conjecture is that the expectation threshold is defined by quantifying over all possible witnesses. And so it's the largest value of P for which there exists a witness. And unfortunately, the conjecture doesn't tell us what the correct witness is. And so it seems very hard to get started thinking about the conjecture because we have no idea what the right witness G is. So it becomes difficult to figure out where to start. And it's at this point that what Talagrand had to say about this starts to become relevant. So Talagrand had a rather nice and natural idea, if you're an analyst. And Talagrand's idea was the following. He says, ignore this witness G that you have to find earlier. And instead of looking at witnesses G that are families inside the power set of X, instead, allow yourself to look at fractional set systems, or equivalently, functions that go into the interval 0, 1, as opposed to looking at functions that take on values either 0 or 1. So what would that mean? It would mean back here that instead of demanding that F lives inside this upset, you'd say that the weight underneath any element in F, when you add up the little G values below it, is at least 1. And similarly, the second condition would just be the weighted sum with little g would be at most a half. So Talagrand proposes a fractional relaxation of what it means to find a witness. Namely, he says, let's find a fractional witness instead. Of course, that works just as well as a normal witness in terms of giving a lower bound on the threshold. The same exact computation that I showed you earlier will show you that if you have a fractional witness at some density P, that also gives you a simple lower bound on the threshold of F. And again, we define the fractional expectation threshold, Q star of F, to be the largest value of P for which there might be such a fractional witness, little g. So it's the largest value of P for which you can use the first moment method to lower bound the threshold, but this time you allow yourself sort of fractional witnesses. Okay. Of course, you've allowed yourself a little more elbow room, so Q star captures everything that you can do with Q and a little more. So clearly Q star is at least Q, and as I said, it also gives us a lower bound on PC, so we have this chain of inequalities. So if PC is the threshold of an increasing family, then you get two lower bounds, Q star and Q, with Q star being slightly more refined than the lower bound that you'd get with Q. And Talagrand says, let's work with Q star instead. And he conjectured that the thresholds at most Q star, again, need not be tight, as we saw with perfect matchings, though I didn't quite compute it. He says PC might not be upper bounded by Q star, but Q star is certainly going to be close to an upper bound. At most, it's going to be off by a factor of a logarithm. But he strengthens the conjecture slightly, strengthens Kahn and Kalai slightly by saying that the logarithmic correction need not depend on the size of the entire universe X that we're working over, but all that matters really is the largest size of a minimal element of F. So for example, when we were looking at K4s, the upset was generated by all the copies of K4 inside the complete graph, in which case L of F just happens to be 4. So in that sort of example, Talagrand predicts that there's no logarithmic gap that one might expect to see, whereas in the case of the perfect matchings, L of F is going to be n over 2, so it does sort of agree with everything we've seen so far. So this is what Talagrand conjectured. Sorry. And this is what we proved. So with Keith Frankston, Jeff Kahn, and Jin Young Park, apologies, I've clearly got someone's initial wrong there. Sorry, that should be a P, not an S. So yeah, with Keith, Jeff, and Jin Young, we've shown that this is true. And the nice thing about what we proved, this conjecture of Talagrand's, is that whilst it doesn't quite prove the Kahn and Kalai expectation threshold conjecture, it seems to give pretty much every known application of Kahn and Kalai. So all the hard instances of Kahn and Kalai that I mentioned earlier, Shamir's problem or bounded degree spanning trees, we get more or less for free. And the reason for this is quite simple. Just that in every example that we know of, the expectation threshold and the fractional expectation threshold seem to more or less be the same. And so proving Talagrand's conjecture happens to yield happily all these applications in those cases. But in some sense, this is not a coincidence. Talagrand conjectures that his weakening isn't that much of a weakening, and that for every increasing family, you don't really gain much by looking at these fractional witnesses. Or in other words, that the expectation threshold and the fractional expectation threshold are never more than constant factors above. So if this can be proved, then this would imply the Kahn and Kalai expectation threshold conjecture as a consequence of our proof of Talagrand's conjecture. Okay, good. Why bother with Q star? So as I said, the main issue with working with the expectation threshold is that there's no idea what the correct witness is. But it turns out the nice thing about working with Q star is that Q star is defined in terms of a bunch of linear constraints, not integer valued constraints. And because these are nice linear constraints, one can quickly apply duality and get an alternative characterization of the fractional expectation threshold. And I won't give you the details, but it turns out it's very easy to show that the dual characterization of the fractional expectation threshold is as follows. It's the smallest value. Remember that the fractional expectation threshold as defined was the largest value of P for which something happened. So unsurprisingly, the dual formulation is going to be, it's the smallest value of rho for which F contains a rho spread, contains the upset over a rho spread hypergraph H. So I haven't told you what these things are. I'll get to it in a second, but there is this nice dual characterization of the fractional expectation threshold. So let's get into understanding what this characterization actually means. So I'll define what it means for a hypergraph to be rho spread. Indeed, that's the notion appearing right here. So we say that a hypergraph, strictly speaking, will allow multiple edges, so it's just a multi-set inside 2 to the x. And we'll say that this is rho spread if the fraction of h inside any upset over some s is at most rho to the s times the size of h. So in some sense, h is well distributed inside 2 to the x. If you look over any particular set s, if you look at how much of h lands in the upset about that s, it decays quite quickly as you fix more and more points in s. And in fact, it decays like rho to the s. Okay, so that's what it means for a hypergraph to be rho spread, that in some sense, quantified by rho, it's well spread throughout the universe. And with that said, just going back and staring at this dual characterization, Q star is then the smallest value of rho for which F contains the upset generated by some rho spread H. And notice, of course, that as rho gets smaller, this condition is stronger. It's saying that things get more and more well spread for smaller and smaller values of rho. The fraction inside any particular part of the world is decaying faster as rho gets smaller. Okay. So that's the dual characterization of the fractional expectation threshold. And this was something that Talagrand observed. This is nothing new. And this is the formulation that we'll use. So what we actually show, and it turns out the two things are equivalent. Talagrand's conjecture is equivalent to the statement, namely that if I give you a rho spread hypergraph, then if I take a random set of density rho times a logarithmic correction, well, that x again will get replaced by the minimal elements, or the largest size of an element in H, but at least for the purposes of the talk, a logarithmic correction, so a random set of density rho times log x, will end up containing some set in your hypergraph. Okay, and that's good because remember, F contains this upset over the hypergraph, so as long as you end up containing some element of this H in your random set, you've done what you were hoping to accomplish. Okay, and I should emphasize that a very nice idea in the proof was introduced by Ryan Always, Shahar, Loet, Wu, and Zhang when they had a recent breakthrough on the sunflower conjecture. So the key idea in the proof is something that these guys introduced while studying the sunflower problem. And I'll try and sketch what that key idea is when I get there. But before I jump into the proof, let me try and sort of say something about question 2. So we stopped before jumping into expectation thresholds and the like, we stopped by sort of observing that we get a lower bound of 1 over n from the first moment computation, but we didn't really say anything about upper bounds. I just told you that Erdős and Renyi worked out the log n over n is the answer. Let me show you how you get that from our proof of Talagrand's conjecture. So the lower bound is straightforward. It's easy to see that you might not have perfect matchings all the way up to log n over n because of isolated vertices. So all we really want to do is to show that the threshold for perfect matchings is no bigger than log n over n. By our theorem, since this threshold probability PC is bounded about by q star times log n, it's enough to bound the fractional expectation threshold of the increasing family corresponding to containing a perfect matching, and to show that that's at most 1 over n, because then we get that the threshold's at most log n times q star, and they'd be done. Okay, and by our dual characterization of q star, and by our I mean Talagrand's of course, it's enough to find a nice well-spread hypergraph living inside this upset, right? And that's easy to do. So all we need is a 1 over n spread hypergraph whose the upset generated by which is inside this family. And the candidate for H is easy. We just take H to be all perfect matchings of inside the complete graph. And we claim that this works. So I haven't written down the calculations, but in this case, the obvious guess for H works. And it's easy to think about why the hypergraph of all perfect matchings is about 1 over n spread. The number of perfect matchings, as we saw earlier, is roughly like n to the n. And for example, the number of perfect matchings over a particular edge, or equivalently the number of perfect matchings going over a particular edge, scales like n to the n minus 1. Well, I'm lying here. That wasn't an n in the exponent, but it's easy to see that this thing is in fact 1 over n spread. It's probably e over n spread if I remember the calculations correctly. And there we have it. It's easy that it follows immediately that the threshold for perfect matchings is at most log n over n. And one nice thing about this very simple calculation is that it generalizes immediately to hypergraphs. All we need to show what the threshold for perfect matchings in R uniform hypergraphs is at most log n over, let's say, n to the r minus 1, is to show that the fractional expectation threshold is 1 over n to the r minus 1. And that's easy. The same calculation that shows that the hypergraph of all perfect matchings in the complete normal 2 graph is 1 over n spread, in fact, shows that the family of all, let's say, perfect matchings in the complete 3 uniform hypergraph is 1 over n squared spread. And so that immediately solves Shamir's problem, which, as I told you before, is a hard theorem of Johansen, Kahn, and Wu. It's serious math. And it turns out this result ends up proving a lot of other things very cheaply. So for example, it gives us the thresholds for any bounded degree spanning tree with almost no work. All one has to do is to compute the spread of all the copies of your favorite tree, the hypergraph formed by taking all the copies of your favorite tree. And these, I should emphasize, though I didn't show you this because I was hoping to write, but I sort of messed up a little bit, is that these expectation threshold calculations are easy. So if I typically give you a graph and ask, or a hypergraph, and I ask you to work out what the spread of this object is, that's an easy computation. We're trying to work out what the threshold is, typically a hard computation. So the point is that the result reduces these hard computations to easy computations. And that's what happens with a bunch of these things, with bounded degree spanning trees, with Hamilton cycles of various sorts and hypergraphs. It also works out the answer to bounded degree graphs. So if I give you an arbitrary n-vertex graph where all the vertex degrees are at most d, when can you promise me that this graph lives inside GNP? And there's a natural guess. One would imagine that a union of a bunch of cliques where each clique is size d+1, so all the vertices of degree d, that would be the hardest graph to find. And our theorem implies that that is indeed true. So as soon as you're likely enough to find that, you'll find everything else. And you get a bunch of things like this, more or less for free from Talagrand's conjecture. Okay, I've got about 20 minutes. So I'll finish with a couple of things. I thought I'd also show you a different sort of application of the theorem, not just from probabilistic combinatorics, but from statistical physics. So here's what's called the two-dimensional assignment problem. It's a really rather simple question. And the assignment problem starts with the following setup. You start with an n by n grid. And let's say you put a uniform, for concreteness, exponential weight at each of these points. The distribution doesn't really matter. Just fix your favorite probability distribution and lay down independent weights on all the points of the n by n grid. Okay. And what we'd like to do now is to select n points, one from each row and one from each column. Or in other words, a permutation matrix from in here. And we want to minimize the weight of the endpoints, the total weight of our selection. So my notation here then is Z2 is the minimum sum of weights over all such potential assignments, quote unquote. Okay. What can we say about the expectation of Z2? So here's a trivial and cheap sort of lower bound. Look at, let's say, just the first row. The smallest weight in there is the minimum of n independent exponentials. So it's going to be on the scale of 1 over n. And that's the case with any row. So even if I cheat and pick the minimum weight from each row, ignoring the constraint that these also have to be in distinct columns, I see that I can't do any better than 1 over n per row, and that'll add up to about 1. So we have a cheap lower bound on the expectation of roughly 1. But much more is known. This problem is well studied. I'll not bother you with the long and sort of glorious history of this problem, but I will sort of mention a very lovely result of David Aldous' that says that actually asymptotically Z2 is pi squared over 6. It's zeta of something. I'm failing to remember. Probably let me not guess incorrectly. So this problem is very well understood in 2 dimensions. But let's ask the same question in 3 or more dimensions. So the setup's the same. We now put independent x1 weights on, let's say, the n by n grid. And we'd like to again select endpoints. And earlier we had constraints on all the lines, the rows and columns. Now we'll insist that we meet each axis parallel plane exactly once. And so the same cheap argument from earlier works. Let's partition the universe into n parallel planes along, let's say, the perpendicular to the z-axis. Well, the minimum weight in any such plane is going to be on the scale of 1 over n squared. It's just the minimum of n squared independent exponentials. And so if you add them all up, you'll see at most 1 over n, oh sorry, at least 1 over n. And that's a trivial lower bound in the same spirit for Z3. But no matching upper bounds were known. So Fries and Sorkin showed that it's at most 1 over n times logarithmic correction. But it's conjectured that this trivial lower bound should in fact be the answer. And a nice consequence of what we've shown is that the framework that we developed to study these things, it usually translates over to smoother settings like the one here. So in the original setup, we were looking at product spaces with products of, of the Bernoulli distribution, which is discrete and has discontinuities. Whereas now we're looking at the product space of a bunch of exponentials. And it turns out in these smoother sort of spaces, these logarithmic corrections are unnecessary. And it comes out from our proof methods that in this sort of setup, one doesn't need a logarithmic correction. This 1 over n type lower bound, which morally is just an expectation threshold type argument, is in fact the truth. So we have a general theorem that says that that sort of thing is the answer up to universal constants. And in particular, for the high dimensional assignment problems, the answer scales like 1 over n to the r minus 1. Apologies again, that S should be a P. So this is again in the same sort of paper with Pete, Jeff, and Jin Young. Okay, I'll finish up with mumbling something about how the proof works. All I'll do really is sketch the lovely idea that always Lovett, Wu, and Zhang had in their Sunflowers paper. I won't have time to sort of go into what we do to refine it and things like that, but it's a lovely idea in its own right, just on its own, and it's worth knowing. So I'll try and say something about their idea, because it is the starting point of our proof is there. Okay, so let's remember our goal. Our goal is to show that a random set lies a random set contains some element of our row spread hypergraph H, right? So what we'll do is that we'll build up our random set in a bunch of bytes. So we'll sort of nibble away. We'll build our random set up in multiple rounds, each time adding a small random set to the aggregate and growing out a random set that way. And so in this picture, W is what we've built of the random set so far. One of my quotes seems to be missing, but so it's a sort of random byte of the universe. And here's a typical member of my hypergraph. And what I would love to see is exactly something like this picture over here, namely that W sort of bites off a good chunk of S. Because if that happens for a typical element of S, we can iterate and say, every time we add a small random piece to our random set, we're biting off a good chunk of a typical set in our hypergraph. And as a result, we're making progress towards our dream, which is to contain some set in our hypergraph H, right? So that's the dream. But of course, that's sort of hogwash. This is not going to happen. Typically, what you're going to see is something like this picture. So if you look at a typical set from your hypergraph and this random byte W here, it'll sort of slice off a tiny sliver of S. And the typical S won't really sort of have much bitten out of it. But in some sense, this is not a problem. Remember that our goal is not to contain most of the elements in H. It's to contain a single element in our hypergraph. So whilst this is an obstacle towards the proof, it's not a moral obstacle towards what we're trying to accomplish. And so the clever idea in the sum class breakthrough is the following. You sort of look at the picture and you say, I don't care that I didn't take a big bite out of S. I'll be happy if I took a big bite out of some other set S prime with the additional property that whatever's left of S prime, this light blue region over here, lives inside whatever's left of S after I take this random bite W. And why should you be happy here? Because once you've taken this random bite W, there's no reason to ever try and find S minus W in the rest of the random set that you build up, right? Because you might as well just find S prime minus W. It's a strict subset, smaller, so you might as well try and find that guy. And that's what one does. It turns out, thankfully, that this is true typically. If you look at a typical set S, there will be some other set S prime that looks like this, which shrinks much better when you take a random bite W, with the additional property that whatever's left of S prime after you remove W lives inside whatever's left of S after you remove W. And so why is this good? Just ignore S minus W and replace it with S prime minus W. And one has to show that this will typically keep the spread unchanged and things like that, but this can be done. The idea is what is important. It's a gorgeous idea. You sort of say the first sort of naive thing, which is to try and shrink every set, is hopeless, but that's fine. You shouldn't be trying to do that. So this is a lovely idea in the sum class paper. Okay. I'll wrap up with saying that much about the proof, and I'll maybe mention a couple of open problems before I end. So of course, the obvious thing that's still sort of staring us in the face is the expectation threshold conjecture. So we've shown the fractional relaxation of it, but we haven't proved the conjecture as such. It's good enough for applications, but of course, it would be nice to know the whole thing. And at the moment, it seems like the best way of proving it is to prove Talagrand's sort of conjecture, saying that the fractional expectation threshold and the expectation threshold are the same up to absolute constants. Because if we can prove that, as I said, that would imply the expectation threshold conjecture. Okay, and there are still some open problems concerning universality type phenomena that I didn't really have a chance to touch upon. And maybe I'll say a brief word about what I mean here. Typically, when one shows, let's say that a random graph has your favorite big spanning tree, one can typically show much more than that. Namely that not only do you contain that particular fat spanning tree with high probability, you'll end up containing every single spanning tree that you sort of care about simultaneously. So not only do you get your favorite thing, you get all of your favorite things at the same time. I would imagine that this should be able to prove things like that, but we don't know how at the moment. And the reason for that is quite simple, and it goes back to something I lied about earlier. So I said that whenever you want to compute the spread of something, that's usually an easy calculation. Well, here's an example of a case where we don't know how to compute the spread of something. Namely, take the hypergraph of quote unquote all universal graphs, universal in various senses of the word. Maybe they contain all sorts of spanning trees or all sorts of bounded degree graphs. And that gives you a hypergraph on the ground set of the edges of the complete graph. If one can work out the spread of these objects, or equivalently the fractional expectation threshold associated with this increasing family, one would be able to recover universality results from our proof of Talagrand's conjecture, but we don't know how to compute the spreads of such objects. In a similar sort of vein, the results that we've got should be strong enough in principle to answer questions of the following form, namely, take a random 3-uniform hypergraph, and you can ask, when will it contain a Steiner triple system? And as I say, in principle, our results should be strong enough to answer it. But what it would need as an input are counting estimates, or equivalently, some understanding of the spread of the hypergraph of all Steiner triple systems. And there's some pretty good results due to, I believe, Lineal and Luria and Kivash is from below and above, or maybe above and below. I think Peter gave lower bounds on the number of these things, and Nati and Zev bounded the number of these things from above. And from the point of view of enumeration, these bounds are very good, but they're not strong enough, unfortunately, to work out the spread. And if one can sort of tighten up those bounds and work out the spread, we'd be able to answer questions about when designs start turning up in hypergraphs, in random hypergraphs and things like that. But unfortunately, the enumerative sort of estimates are not good enough at the moment to be able to answer those questions. So those sorts of things still remain open, and answering those things would be very interesting. I'll mention one final thing, given that I've got a couple more minutes. And it goes back to the expectation threshold conjecture. And I mentioned this sort of very briefly when I was talking about it, when I was talking about perfect matchings. So the motivation behind the way I understand it, the expectation threshold conjecture, came from looking at this coupon collector type behavior. So this logarithmic correction isn't just a thing that turns up in examples, but it's also a thing that we have some understanding of. The log n comes from saying, oh, there's a coupon collector problem that's slowing down the appearance of whatever you're interested in. But our results don't seem to suggest any particular coupon collector type problem as a natural obstacle for any given increasing property that you're interested in. And there are various sort of threshold problems where the logarithmic corrections are fractional powers of log. So the coupon collector problems causing these delays are slightly subtler, but our proof seems to give us no sort of general understanding of where this logarithmic gap is coming from. And that would also be something that would be very sort of worthwhile to understand. Okay, I'll stop here.
Okay, thank you very much indeed, Bhargav, for a lovely talk. So we can have a little, a few questions. If people would please let us know in the chat if you'd like to ask a question. We have a couple of questions already. Actually, let me start by asking something myself, which is, so how would it work if you wanted to apply this, for instance, to directive graphs, or something like satisfiability? If you had an instance of k-sat, does it adjust to that circumstance?
So I think for SAT, it would sort of obviously say something, because those are monotone problems. Changing a no to a yes is good for SAT. Oh, actually, I think, is that right? The general setup, it's not, is it? So when people study SAT, I assume they're looking at clauses where you don't do nots. I don't know precisely how the setup is. But if it's not monotone, then this says nothing, because the p-biased measure is not an increasing function. If it is monotone, it will give you something, but my understanding is that much more precise things are known. This will give you answers up to multiplicative constants, but I believe people understand the asymptotics of the threshold over a sequence of like long, hard sort of bits of work, but I think the understanding is maybe better already than what we might be able to show. But I'm not an expert, so don't hold me to that.
Okay, thank you. Let me, so for the questions, I'll unmute people one at a time. So Aglos first, you should be unmuted.
Yes, thank you. So when you talked about the statistical mechanics problem, where you had these exponential random variables, could you state your theorem in this case? So what do you mean by expectation threshold, for example?
Sure. So what we consider is the following. So we consider the following sort of, what's the word for it? We consider the following sort of hypergraph type stochastic process, and we study the extrema of it. And what I mean is the following. So take a ground set, put random weights on each of those points, let's say random x1 variables, and you start with a hypergraph and you look at the edge of the smallest weight. So you study that problem. And you ask, what can I say about this? It turns out the answer is more or less the spread of that hypergraph. So that's the general statement. So you try and understand the fractional expectation threshold of the family of sets over which you're minimizing. Does that help? Yeah, so there the logarithm disappears. When you have smoother distributions, you don't need this logarithmic correction.
Okay, and let me pass over to Victor next. Victor, you should be unmuted.
Oh, thank you very much, Bhargav, for a lovely talk. That was really enjoyable. Yeah, this was really fun. I had a questions again. Also, you started answering this. This is about also when you need the logarithmic corrections.
Sure.
I was wondering if there are general heuristics or the general results which say, okay, if your family satisfies this and that property, then you don't need a logarithmic correction. For example, if you have a locally defined property, like containing K4 being an obvious example.
Sure. So unfortunately, the short answer is we learn almost nothing from our proof. So of course, the one thing we learn is that if the minimal elements of this upset are all small, right, then you don't need the logarithm.
Yeah, okay. So that's the kind of local.
Yeah. But there are examples of upsets where the minimal elements are all big, where you don't need a logarithmic correction, and this doesn't say anything about things like that. For example, I believe there are results of Oliver's about finding certain spanning subgraphs where the moment tells you the answer. The first moment tells you the exact answer, and it's done by a second moment calculation. But these sort of results wouldn't tell you that. They wouldn't be able to detect the lack of this logarithmic gap. And I'd be very curious to understand in some sort of less miraculous way where that log is coming from. I mean, I can tell you where it comes up in the proof, but that's unenlightening, I think.
And do you think actually there's any possible behavior between constant and log? So,
oh, there are examples where the gap is in between, right? So for example, when you ask, when does a random graph contain a triangle factor?
Right.
The logarithmic gap is something like log to the 1/3 or 2/3. I don't remember immediately off the top of my head, but that's not a constant, nor is it the full log. But so where is that coming from? Right. I mean, we know where it's coming from by looking at the problem, but our proof wouldn't give you that.
Okay, oh, that's really intriguing. Oh, thanks a lot. I think that's a great answer to my questions.
Okay, let me pass to Oliver next.
Okay, on the fractional expectation threshold thing, are there examples you know about where you sort of know what it is, but it's not just the simple thing that you're looking for something and your property H is all copies of that something? You see what I mean?
I haven't thought very hard about it. I just know that when one tries, so it's very rare that one computes these things exactly. One usually settles for bounds on both sides up to constant. And every known example, I think even the constant between the fractional expectation threshold and the expectation threshold is quite small. So for all I know, that constant could be, like 2 or something.
But my question was a bit of a different one. So in principle, the H that you use to bound the fractional expectation threshold, you don't know what it is. But in the examples, it's a sort of, you said it's the obvious thing for matchings or whatever.
Do
you have examples where it's not such an obvious thing or not?
I think the sort of thing I was mumbling about with K-force would be the same sort of thing. Like if you've got a pendant edge.
Yeah. Okay. Yeah.
Look at smaller things. Yeah.
Yeah. Mm-hmm.
So you do need to give yourself this wiggle room, unfortunately. So there is this quantifier. So I'll mention, given that you brought this up, there is one sort of case where one has a good guess for what these things ought to be. Namely, when you're looking for copies of a particular graph, there it seems like the only things that should matter are subgraphs and whether you can find them all. But I don't think we know the equivalence of these two formulations.
Okay. Okay.
The conjecture is that the obvious witnesses are the only ones you have to consider.
Yeah.
But we don't know that.
Okay.
Okay. Next question is from Ron. Whoops.
Hi, Bhargav. Thanks a lot for the very nice talk. You mentioned at the end about finding a Steiner triple system inside, I guess, a random uniform hypergraph. Was that? And could you elaborate on how that would follow? Would it follow from the statement, from the methods?
Right. So it would follow from the result. If one knew very precise counting results about how many of these things there were.
How would it follow from the result?
So here's what you do. You think about the hypergraph. So now our universe are all triples on n, let's say. And you look at the hypergraph, each of whose edges are Steiner triple systems. Okay, so we're interested in the threshold of the increasing family generated by this hypergraph. So that's what we're trying to understand.
I see.
And by our result, it's enough to understand the spread of this hypergraph. So
all right, I see. I see. The universe is a complicated universe, and then the spread is a bit hard to see, but very good. Thanks.
Yeah. But the spread, it looks like it should be what one guesses. So there are results of Peters and of Nati and Zur that sort of give complementary sort of bounds that look like 1 plus minus epsilon something to a big exponent. But the problem is that error in the base of the exponent is too big to be able to try and understand the spread. So you need much more fine-grained counting results.
Thanks a lot.
No problem.
Okay, and next question from Ryan.
Ryan?
Okay, we seem to...
We can't hear you.
Okay, right, Ryan. I did unmute you, but you're unmuted again now.
Can you hear me now?
Yes.
Yeah.
Okay. So I wanted to ask if there are any interesting threshold properties for which you get an equality case of our theorem, because the only reason we know that, we only have basically one equality case of why you need the log, that everything basically comes from this grid example. So if you just look at, your perfect matching of everything, or one of the other graphs for which the logarithmic factor is necessary, can you find any interesting set systems for which this log factor is necessary?
I'm not sure I understood the question, actually. What do you mean by equality cases?
Oh, okay, I mean, you clearly need this log factor in our theorem.
Sure.
And that we have examples showing this log factor is tight. But we only have like a very restricted set of examples that show that this log factor is tight.
Sure.
So I was wondering if there are any interesting examples that just come from taking something like a perfect matching of everything and looking at and just going through the fractional expectation threshold, and somehow you can like reverse engineer a set system that witnesses why you can't do better than log in our theorem.
That witnesses why you can't do better than log.
Because
No,
you only
so,
have like.
so in some sense, I'm not sure I completely understand, but I'll still sort of speculate and sort of say no, in that this log is speculatively coming from a coupon collector type probabilistic reason, but I don't think we know of any examples where the log is necessary and we don't have a simple explanation for the log. There are more complicated examples where you need this log that you might find interesting. If you look up, I believe, results of Kriver-Levitch's on larger degree spanning trees, there are some interesting examples there. But in some sense, at the heart of everything, there seems to be some sort of coupon collector. But I don't think, I don't know if that answers your question in any way. Okay.
Yeah, just if you can reverse engineer a set system from some of these examples, I don't know.
Yeah, I don't know. Yeah, what you
like if you go back and look at the Rutgers perfect matchings, and then you figure out what set system this actually gives you.
I mean, that is the set system, right? You look at.
Yeah, okay. It is a set system.
Yeah,
but
it's just a bigger universe. Yeah.
Okay, I have to think about it, but I think it would tell us something interesting that we don't already know about why you can't, because we, as I said, we have basically one equality case showing why log is the right answer, and it would just be interesting to have other set systems that for which that show that you need this log that don't look anything like the examples.
So if you go around looking at many of these threshold results for spanning structures in random graphs or random hypergraphs, you get loads of examples. And you can always translate them back into set system language by thinking of the universe as the edges of the complete graph.
Okay, maybe this is a good point to stop.